Hello everyone, my name is Naitikkumar Mistry and I'm here to present a YouTube presentation on do incentives build robustness in BitTorrent. This research paper was written by Michael Pitek, Thomas Isdale, Thomas Anderson, Arvind Krishnamurthy and Arun Venkataramani. And this paper was written by these students who were the students of the University of Washington, and they were awarded as the best, and this research paper was awarded as the best student paper. Okay, so let's go ahead. Here what we're gonna cover is we'll talk about the introduction, then we will introduce BitTorrent, then we will talk about monitoring altruism in BitTorrent, and we will introduce another new client, BitTyrant, on which this research paper was written on. Then we will talk about the evaluation, then we will show the related work, and we will move to the conclusion. Okay, let's get started. Okay, so here a fundamental problem with the many peer-to-peer system is the tendency for user to a free ride, which means to consume resources and resources without contributing to the system. Suppose that you are downloading any movie from any server and you are just downloading and you are not giving anything to the or you are not contributing anything towards the server or towards the group of the people who involved with this. So popular BitTorrent client is an example to solve this problem. As we all know, it uses the tit for tat reciprocity. That means you get something when you give something. This method to give the positive incentive to the user who contribute these resources. Though BitTorrent is successful, this research paper shows that this is not robust to the strategic client. Here BitTyrant come for the solution. BitTyrant is a modified BitTorrent client designed to benefit the strategic peers. The key idea of the BitTyrant is they carefully select peers and contribution rates. Robustness required that performance which does not degrade. It discovered the presence of significant altruism with BitTorrent and unnecessary contribution that can be relocated to improve the performance for strategic clients. Okay. So what is the BitTorrent? So BitTorrent is a true peer-to-peer sharing protocol, as we know. There means there is no central server like the Napster. Moreover, the bilateral nature of the tit-for-tat allows for the enforcement without a centralized any trusted infrastructure that we just talk about. There is no central server in there. Here I would like to introduce some terminology which BitTorrent use. The first one, it is the swarm. Swarm is nothing but the group of uh, peers who are actually sharing the torrent. The tracker. So what tracker is work as a centralized tracker which track all the active peers in the same group or same swarm. The seeds is the users who are in the possession of the complete file. The local neighborhood is nothing but the set of directly connected peers. So suppose there is two people who are directly connected with each other with the peer-to-peer system. Those are considered in the same local neighborhood. Active set. The active set is a set of peer to which BitTorrent client is currently sending the data. So same example again, there are a couple of people who are in the local neighborhood and they are sharing with, they both have the BitTorrent client and they are currently sending data. So the group of people, those kind of group of people or peers, those are considered that they are in the active sets. Each round, a peer sends data to unchoke peers from which it received the data most rapidly in the recent past. This strategy is intended to provide positive incentive for contributing to the system and inhibited free riding. However, Client also send data to a small number of randomly chosen peers who have not earned the status of unchoked peers. Such peers are said to be optimistically unchoked peers. Peers that do not send data quickly enough to earn reciprocation are removed from the active set during the tit-for-tat round and are said to be the chalk. So the chalk peers are the peers that do not send the data quickly enough. Each peer provides an equal share of its available upload capacity to peers to which it is actively sending the data, and we will call this as an equal split fate. Active set size is proportional to the upload under root of the upload capacity. Also, BitTorrent's behavior depends on the large number of parameters that that are topology, bandwidth, block size, churn, data availability, number of directly connected peers, active TFT transfers, and number of optimistic unchokes. Okay, so now let's talk about how BitTorrent works. Suppose that there is a central server from which you want to download a video file, and there are multiple users. Also, they also want to download the same file that you are downloading right now. So the number of people who using that servers is increases, and suppose that the server crash, and so nobody can get a file. So how does the peer-to-peer system work is something like BitTorrent, that they uh, they create a broken pieces of the full data. Suppose here we have in this figure we have 4 peers, that is 4 users who are having BitTorrent client. Suppose the peer 1 has the full data, like all the pieces of the full video file. Suppose that the video file. So 1, 2, 3, 4, all the pieces they have. He have. On peer 2, he only he only has the broken piece of number 1 and the number 4. He does not have number 2 and number 3. On peer 3, he only has the number 1. He does not have 2, 3. He does not have 2, 3 and 4. On peer 4, he has only the 1, 2, but he does not have 3, but he has the 4. So what tracker does here, tracker keep tracks of everything, like which peer has which information, like peer 1 has everything, peer 2 has something, peer 3 has something, and peer 4 has something. And it will keep communicating the between the peers. As soon as the new client joins here, as soon as the new BitTorrent client joins here, the tracker introduces this client to the among the all the peers. So now tracker has all the information of all the peers, like connected all the 5 peers, and they can the peers among them, they can download any data file. Like suppose the new peer is asked for the broken piece of number 1, then it goes to the tracker. The tracker contacts all of the peers, and the peers replies that I have one, I have one, I have one, and I have one, and it will be randomly chosen any of the peer, and it will download it from there. Also, it contributes to the group of peers too. Suppose that peer 3 does not have the broken piece of number 4, then all peer 1, peer 2, peer 4, and as well as our new peer will also contribute to them and say to the tracker that I have that information if we want to download from here. So that's how the BitTorrent works. Okay, let's move on. So now let's talk about the modeling altruism in BitTorrent. In this section, we examine 2 questions relevant to understanding how incentives impact performance in BitTorrent. So in first case, let's introduce altruism. Altruism are the any upload contribution that can be withdrawn without loss in download performance. And we are Based on that, we are make several assumptions to simplify our analysis and provide a conservative bound on altruism. So first one is the representative distribution. The distribution of a typical group may not be identical. For an example, the high capacity peers tend to finish more quickly than low capacity peers, but they may also join more the group of peers simultaneously. If they join only a single group of peers and leave shortly after the completion, the relative proportion of how capacity peers would increase over the lifetime of a swan. Second one is uniform sizing. Peers other than the modified client use the active set sizing recommended by the reference BitTorrent implementation. In practice, other BitTorrent implementation are the most popular and have the different active sizes. As the aggressive active set sizes tend to decrease the altruism, and the reference implementation use the most aggressive strategy among the popular implementations as this research paper inspected. As a result, this BitTyrant as a model provides a conservative estimate of altruism. The third one is the no steady state. No steady state can explain as the active sets are comprised of peers with random draws from the overall upload capacity distribution. If churn is low, over time, tit for tat may match peers with similar equal split rates. Biasing active sets draw. We argue in the next section that the BitTorrent is slow at the steady state, particularly for high capacity. Uh, Now, the fourth one is high block availability. Some performance is limited by the upload capacity. That is, peer will always be able to find interesting data to download. This research paper finds that although the reference BitTorrent implementation is designed to ensure high availability of interesting blocks, in general in practical life, the static active set sizing in some clients may degrade the block availability for high capacity peers. These assumptions allow us to model altruism in BitTorrent in terms of the upload capacity distribution only. Okay, so now let's talk about the tit for tat strategy. So by default, the BitTorrent client optimistically unchokes two peers every 30 seconds to explore the local neighborhood for better reciprocation pairings. Since all the peers are performing this exploration concurrently, every 30 seconds a peer can expect to explore two candidate peers and be explored by two candidate peers. So two peers find you as well as that other two peers that you found also finds you and the other peers. Since the equal split capacity distribution, we know that and we can express the probability of finding a peer with the equal or greater equal split capacity. Suppose in a given number of 30 seconds round. Taking the expectation and multiplying it by the size of the active set gives an estimate of how long a new peer will have to wait before filing its active set with such peers. This result suggests that tit for tat as implemented in BitTorrent does not quickly find good matches for high capacity peers. For an example, a peer with 600 and suppose that 6.4 Mbps upload capacity would transfer more than 4 GB of data before reaching to the steady state. The long convergence time suggests a potential source of altruism, which is the high capacity clients are forced to peer with those of low capacity while searching for the better peers via optimistic unchokes. Okay, now let's talk about the possibility of reciprocation. So for that, uh, suppose there's a node Q sends data only to those peers in its active transfer set, which is reevaluated at every 10 seconds. So that's an every round which start at every 10 seconds. If a peer P sends data to Q at a rate fast enough to merit the inclusion in Q's active transfer set, P will receive data during the next tit for tat round, and we say Q reciprocates with P. So the reciprocation from Q to P is determined by the two factors. First one is the rate at which P sends data to Q, and the second one is the rate at which the other peer sends data to Q. If all other peers in this Q's current active set send at the rates greater than the P, the Q will not reciprocate with the P. Okay, so let's now see this figure right here. So here is the graph of expectation of reciprocation probability that we just talked about versus the bandwidth. Here is the equal split capacity, which is shown by this red continuous line, and the upload capacity is the blue continuous line. Here there is a sharp jump you can see, and you can see from here in reciprocation probability suggest a potential source of altruism in BitTorrent. So equal split bandwidth allocation among the peers in the active set. We can see here from, as you can follow my mouse pointers, you can see this red line right here. It is the equals. If we consider this line, it shows that if our equal split rate, which is right here, will be if it is greater than 14 kbps, then that peer can have a reciprocation. So consider that this is the 14 kbps of bandwidth right here, and as you can I already talked about this probability, which is right here, and it is, we can see from the figure that it is 1 when we have 14 kbps of the bandwidth, and so the if it is like more than 0.9%, reciprocation probability is more than 0.9%, that is 90%, and uh, it is greater than 14 kbps, then it suggests that we have a further contribution that may be altruistic. Okay, let's move on. Expected download rate. After each TFT round, which is 10 seconds, peer P receive data from the both tit for tat reciprocation and the optimistic unchokes. Reciprocation is possible only from those peers who are in P's active set and depends on P's upload rate, while optimistic unchokes may be received from any peers in P's local neighborhood, which is not concerned with the upload rate. Number of the optimistic unchokes are defaults to the number 2. Here there is a figure of expected download rate into the kbps and the upload capacity into the kbps. There that should be supposed to be like this, but there is a sublinear growth line here, which is the expected performance of the BitTorrent, and here we can see that it's not as the perfect. So the difference at some point of any point where it reached the steady state, the what is the perfect and what we achieve, the difference between these two, if you can follow my mouse pointer, you can see in the figure that the difference of this perfect fairness at steady state and what we achieve at the steady state is the altruism, and this is that from where we can measure the altruism. So in a BitTorrent, for high capacity of peers, there is an unfairness, uh, which is shown by the uh, sublinear path. This unfairness improves performance for the measure of low capacity peers. That suggests that the high capacity peers may be able to better allocate their upload capacity to improve their own performance. Okay, let's talk about the expected upload rate. So we already considered the download performance. Now we talk about the upload contribution. That is, two factors can control the upload rate of the peer. The first one is the data availability, and the second one is the capacity limits. Um, when when a peer is constrained by the data availability, that it doesn't have very good available data, and which is not of the local neighborhood, there in that case this peer's upload capacity is wasted and the utilization suffers because of the dependence of upload utilization on the data availability. It is crucial that a client downloads a new data at a rate very fast enough so that the client can distribute that downloaded data and saturate the upload size. In practice, most popular clients do not follow this dynamic strategy, and instead of that, they making the active set of size configurable but static. And Azure as the BitTorrent client suggests an active set of size is 4. Now let's look at the this figure again. If you can follow my mouse pointer here, this is the number of total peers, and which is shown by the red line, and the blue line is shows the optimistic unchokes. So from here we can see that there is a slow client that never get reciprocated, because if you can follow my mouse pointer, it is I'm sorry, it is less than 14 kbps, and we just talk about that if the speed is bandwidth is less than 14 kbps, the client or peer can never be get reciprocated. And more than 14 kbps, if we talk about the more than 14 kbps client, those are the fast clients who actually pay more and get less. So low bandwidth peers almost never earn reciprocation, while high capacity peers send much faster data than the minimal rate required for the reciprocation. Here, low bandwidth peers, despite not being reciprocated, still receive data in aggregate faster than they send the data. Okay. So this is the problem with the upload and download uh, and in BitTorrent. So to overcome these problems, that they introduced a new client, that is BitTyrant. So the topic that we just told in the while I was explaining the figure. So this is the BitTyrant, a strategic client. BitTyrant is based on the Azure, as Azure is the most popular among the client in terms of traces, which exploit the unfairness and minimize altruism. BitTyrant work as you give the contribution and you will get the performance in the indirect manner. Uh, it will also increase the performance for the low capacity peers too, and BitTorrent dynamically choose how many and which peers to send the data. Okay, so let's move on next. There are three strategies to improve the performance. The first one is the maximize reciprocation bandwidth per connection. So in this strategy, it find peers that reciprocate with the high bandwidth for a low offer rate. Reciprocation bandwidth is depend on its upload capacity and active size. By identifying peers that have large reciprocation bandwidth, a client can optimize for a higher reciprocation bandwidth per connection. Second strategy is the maximize number of reciprocating peers, in which a client can expand its active set to maximize the number of peers that reciprocate until the marginal benefit of an additional peer is outweighed by the cost of reduced reciprocation probability from other peers. The third one and the last one, a strategy is deviate from equal split, on in which on per connection basis, if we talk about, a client can lower its upload contribution to a particular peer as long as that peer continues to reciprocate. The bandwidth savings could then be reallocated to new connections, resulting in an increase in the overall reciprocation throughput. Results show that these strategies are likely to be effective, and the largest source of altruism in this model if there is an unnecessary contribution to a peers in a nodes set. So this is a pretty efficient model with compared to BitTorrent. So now let's see the algorithm right here. In this algorithm, it says that for each peer P, which denotes as a P, it maintains the estimates of expected download performance, which denotes as DP, and upload performance, which denotes as UP. So at the start of the algorithm, initialize the uploading speed and downloading speed, or uploading performance and downloading performance, assuming the bandwidth distribution. Um, Downloading performance is initially the expected equal split capacity of P, and upload performance is initially the rate just above the step in the reciprocation probability. For the each round, the rank order pairs by the ratio of download performance divided by upload performance, the ratio of the download performance and the upload performance, and uncheck those of top rank until the upload capacity is reached. So it says D0. Let's talk at the first peers. Download performance and upload performance is denoted by D0 divided by the U0, D1, U1, D2, D2 and U2's ratio, D3 and U3's ratio, D4 and U4 ratios, and the summation of that, which is less than or equal to capacity. At the end of the each round after 10 seconds and 30 seconds, for each unchoke peer, what will happen if consider the case 1 that if peer P does not unchoke us, so uploading, then the uploading performance is 1 plus delta into uploading performance. The second condition, if peer P unchoke us, then the download performance will be the observed rate, and if peer P has unchoked us for the last round, that R round, that can be the 3, 4, 5, the upload performance is 1 minus the gamma, which is the rounds, into the upload speed. So let's talk about the assumption and characteristic. The download benefit, which is DP, and the upload cost, which is UP, are not known a priori. The update operation dynamically estimates these rates. BitTyrant continues to unchoke peers until it exhausts its upload capacity. User-defined priorities can be implemented by using scaling weights for the DP and UP ratios across the multiple hosts. And okay, so let's talk about the prediction of peer capacity and reciprocation. So in this section, it falls under two categories will fall under this section. The first one is determining upload contribution. So in this BitTyrant implementation, the research paper writers They show that the upload capacity is typically decreased by the 10% if the peer reciprocates after 3 rounds, and increase of 20% if the peer fails to reciprocate after being unchoked in previous round. In estimating reciprocation bandwidth, model consider the average download rate over a tit-for-tat round. It determines the rate of have signal from peer, that is I have this piece of data and this species. It use this as the total upload capacity of the peer. As from the Azure client Azure, it determine the active site size for this upload rate, and using this determine that equals split rate, and they use as the download benefit. Okay, let's talk about the sizing of the neighborhood. The active size is sized to provide the diverse set of data to enable data action without any data availability constraint. So there is a no constraint if you want to exchange the data, and it can extract the more peers by gossip among the peers. It means that contacting the peers which each other with contact with the peers who are in the same local neighborhoods. That way they can extract the more peers. The BitTorrent protocol extension is the push based, but not this one. As the size of the local neighborhood increases, the protocol overhead also increases. It can increase from 0.9% to 1.9% of the total file data has received. That can be additional cheating strategies which can improve the performance, but it is not implemented in this model, because if the client tweaks or do something, that they can actually cheat with this client. But it ha it this model uh, I'm sorry, but additional cheating strategy can be used to improve the performance. The first cheating strategy is exploiting optimistic unchokes. So in this, if a peer has built up a deficit in the number of trades byte, it is likely to be picked for optimistic unchokes. The cheating client disconnect and reconnect with the different client identifiers, and it can be prevented by maintaining the IP address and peer statistic across the disconnections. Second one is downloading from the seeds. So early versions of BitTorrent client used a seeding algorithm wherein seeds upload to peers that are fastest downloaders, and an algorithm that is prone to exploitation by fast peers or client that falsify download rate by emitting have messages. So they can send that I have this actually message, but they don't have. And more recent versions of seeding algorithm that perform unchokes randomly, that spreading the data in a uniform manner, that is more robust to the manipulation. The third one is the falsifying block availability. In this strategy, a client would prefer to unchoke those peers that have blocks that it needs. So by doing this, a peer can appear to be more attractive by the falsifying block announcement and to increase the chances of being unchoked. In practice, in real life, this exploit is not very effective because of the first reason. A client is likely to consider most of its peers interesting given the large number of blocks in a typical group of peers. The second reason is the false announcements could lead to a short-term benefit as a client to unlikely to continue transferring once the cheating peer does not satisfy issue block request. Okay, now let's see the evaluation. The evaluate BitTyrant on real group of people drawn from that is real peers drawn from the popular aggregation sites to measure the performance for a single strategic client. Evaluate sensitivity to various upload rates and measure performance for many BitTyrant peers. Now let's see the performance. I'm sorry, not the performance, but the evaluation of BitTyrant on the single user. So in this figure, you can see that it is the ratio between the downloaded times for an existing Azure client and BitTyrant. And as you can follow this red line with my mouse pointer, it shows that the median performance gain for the BitTyrant is a factor of 1.72. This model expects relative performance gains to be the greater for the clients with the greater upload capacity. Um, BitTorrent is also improves the performance and provides consistent performance across the uh, multiple trials. If and we are talking about the consistency. So this consistency allows peers to detect and reallocate the excess capacity for other users. While we talking about Azure spread of the download times over 6 trial is more, and prediction it is very hard. Okay, and let's evaluate this model on multiple BitTorrent clients. So consider there are two types of the peers. The one is the strategic and another one is the selfish. So any peer that uses the BitTyrant unchocking algorithm is considered as a strategic, and if such a peer withholds contributing excess capacity that does not improve performance, then it is a strategic client as well as the selfish client. BitTyrant and the original unmodified client assume all the users contribute all of their capacity. The capped BitTorrent shows performance that is right here. The blue line, you can, if you follow my mouse pointer, that the blue line is the cap line. It shows the performance that when high capacity selfish peers limit their contribution, when high capacity selfish limit their contribution. Okay. If peer reallocates, the aggregate capacity and average performance are reduced for the low capacity peers, as we can see from the figure that BitTyrant is right here and the original one is right here. So there is a difference at this 0.5 fractional cumulative CTF function that uh, it is actually the less for the BitTyrant. Beyond a certain points of peer that contribute significantly more data do not see the faster download rates. So after some part of some point, after passing of some point, that is after a certain point, the peer that cannot contribute, they do not see the faster download rates and they will keep seeing the lower download rates. Okay, so that was the evaluation, and let's jump to the conclusion. So although there are tit for tat discourages for the free riding, bulk of BitTorrent's performance has little to do with the TFT. Altruistic contribution on the part of a small minority of high capacity peers. BitTorrent works well if no one tries to cheat it, if no one try to apply the any strategies on that, and just use it as BitTorrent documented us to use it. In that way, BitTorrent is perfectly fine. Um, BitTyrant is induced the low bandwidth peers to invest higher bandwidth in seeking of better performance. So BitTyrant is the better version of the BitTorrent. So if someone try to cheat it by uh, showing the low bandwidth with the low bandwidth peers, They have to invest the high bandwidth in seeking of the better performance, which is not possible in the BitTorrent. And there are some uncertainties that leave us with an open question. The two incentives build the robustness in the BitTorrent. Okay, so these are the references that I have made, that I made the PowerPoint presentation from it. And okay, thank you for your time. And any questions, I'll welcome. All right, thank you. Goodbye.